All right, trig students, so a new chapter, and what we're going to be doing here is taking a look at radian applications. There's the big two. We'll take a look at some others later, but the big ones are this concept of arc length and this concept of area. So let's first deal with the arc length. Let's use that, learn from it, and then move from there. With regards to arc length, remember what a radian is we're basically talking about, right, the number of times a radius is in the circumference. Okay, so that's what I described it as in the last section, 3.1. But we're going to refine this idea about, because we're talking about not the entire circumference. We're talking about just pieces of the circumference, if you would. And so that actually is arc length. So here's a circle, right? Here's the center, and here's my radius. Now the entire walk around, right, that's my circumference. But what we, to describe it in anything else, let me change colors here. We're going to call this walk, right, how far you end up walking. So let's just say I walk that far. So what I have in red, we're going to call that S, and that represents what we call the arc length. Of course, that arc length can be really small. It could go all the way around and truly be equal to the circumference. But we're basically talking about how far along did you walk along the circumference. So to find the angle measurement that we've created, right, by doing that little walk, it turns out that the angle, right, is going to be that arc length that we walked divided by r. So again, the idea is how many times does a radius go into the arc length now? Okay, or it's no longer part of the circumference. We're giving it a name. So how many times does a radius go into the arc length, whatever that arc length is? And that gives you your radian measure. So when I have 1 rad, that just basically means that my arc length is 1, my radius is 1, and so my theta is 1 over 1, which gives us 1 rad. If S was equal to 2, right, and R is equal to 1, then that would give us 2 over 1, which would give us 2 rad, and on and on and on. So there's a little handy-dandy formula. Again, as the Greeks noticed, that this ratio is the same no matter how large my circle is. All right, so this radius could be small, it could be big, but if you measure the arc length along the edge that you swept out to create the angle, divide that by r, you are now talking about how many times the radius goes into that arc length. And so you essentially have created your formula for a radian. Another way that this is written, if I took the time to multiply both sides by r, another way that this can be written is that the arc length is basically the radius times my theta. So you decide how you want to look at it. I kind of like this one since there's no fraction in it at the moment, but the arc length that I go is basically the angle that I have times the radius. And then one reminder, this is all good in radian mode. Right? As soon as we walk away from radian mode, all this is off the table. So degrees doesn't quite work here. So whenever we're talking about arc length or the area of a sector, we're automatically assuming that I'm in radian mode. So make sure we have that. And so now we have some formulas, and we can obviously begin to use it. All right, so there's the setting of the stage of arc length. Obviously, I've got a bunch of little made-up problems where we work through that. Sometimes we'll bust out our calculator, sometimes we won't. But how about I leave it at that, and then we'll do a round of calculations using our formulas, all right, in the next video.